Hello. Now that we've talked about the nature of light, we're ready to look at some of the instrumentation astronomers use to study and make sense of the light coming from celestial objects. I've mentioned that most of the information we have about the universe comes from looking solely at light. We collect this light with telescopes and record it with cameras and other instruments. Telescopes and cameras function much like the eye, so it makes sense to first talk about the principles of eyes and cameras. Let's start with the eye. Its basic components are a pupil, lens, and retina. The pupil controls how much light enters the eye. The lens bends light to form an image on the retina, and the retina contains light-sensitive cells called cones and rods that, when triggered by light, send signals to the brain via the optic nerve. Most of the cones are located here on what's called the fovea centralis, or macula. These are rod and cone cells. The cones provide the eye's color sensitivity, whereas the rods are responsible for our dark adapted vision. We have many more rods than cones, about 120 million rods versus 6 to 7 million cones. This is why the world looks in shades of gray and black in low light conditions. When you walk into a dark space, it takes about 10 minutes for your eyes to adjust. This is actually the amount of time that the rods need to activate and take over for the cones. We are able to see dimmer objects in our peripheral vision because that's where the rods dominate. For example, if you see a dim star in your peripheral vision, it may disappear when you look at it directly, since you're moving the image onto the cone-rich fovea region, which is less light sensitive. There's a planetary nebula I like to show at our observatory nights. It's nicknamed the Blinking Planetary. By the way, a planetary nebula is what's left when a star like our Sun runs out of nuclear fuel and blows off its atmosphere. The dead core of the star remains at the center. When you look directly at the blinking planetary through the telescope, you can only see the dead core at the center and not the surrounding atmosphere. But if you look at it with peripheral vision, the nebula part becomes visible. You can make the planetary nebula appear to blink on and off by looking at it indirectly and then directly. The rods of our eyes do not see red. This is why astronomers use red lights in observatories. Since the rods do not respond to red, an astronomer can gain full dark adapted vision in red light. Once your eyes are adjusted to the dark, if you look at anything with a white light even for a moment, you'll have to wait for your eyes to become dark adapted all over again. Red lights won't ruin your night vision like a white light can. The lens in your eye functions the same as the lens in a magnifying glass or a telescope. They all bend light. This bending of light is called refraction. Parallel rays of light, like those coming from a distant star, converge to a point called the focus, or focal point. The fact that parallel rays of light converge to a sharp focus is why distant stars appear as points of light to our eyes or in photographs. Light rays from a nearby object are not parallel, so they will enter the lens from all different directions. These rays do not all converge at the focus, but they do follow the laws of optics as they bend at the lens. The result is the bending of rays to form an image of the original object. The place where the image appears in focus is called the focal plane of the lens. In an eye with perfect vision, the focal plane is on the retina. The image formed by a lens is actually upside down. Our eyes form upside down images, which are then flipped right side up by our brains. If we want to keep an image for study, we need to record it with something. Astronomers use fancy digital cameras to record their images. Inside digital cameras are electronic chips called charge-coupled devices, or CCDs. A CCD is physically divided into grids or pixels. When a photon strikes a pixel, it causes a bit of electric charge to accumulate. Each subsequent photon striking the same pixel adds to this accumulated electric charge. After an exposure is complete, a computer measures the total electric charge in each pixel and determines how many photons have struck each one. The overall image is stored on the memory chip as an array of numbers representing the results from each pixel. The astronomical images you see have, in most cases, been processed. Sometimes the image is manipulated to bring out details that might otherwise remain hidden. Image processing can sharpen or adjust colors, correct exposure issues, and remove defects from an image. The background here is an infrared false color image of hot gas clouds on the outskirts of the Orion Nebula. This is an image of Enceladus, one of Saturn's moons. It's processed to highlight a plume of water ice coming from its surface. I'll leave you with one interesting tidbit of information about the eye. In the 1950s, an Austrian professor named Theodor Erisman had a student assistant, a man named Ivo Kohler, wear a pair of hand-engineered goggles. Inside those goggles, specially arranged mirrors flipped the light that would reach Kohler's eyes, top becoming bottom and bottom top, so that Kohler was seeing the world upside down. At first, he stumbled around, but after a little over a week, his brain compensated and he could function completely as normal with the goggles. He was even able to drive his motorcycle. It's an interesting example of neuroplasticity. Our brains can be quite adaptive. That's it for now. Enjoy your day or your night. I will talk to you soon.